already told him, and
okay, we've got up on the projector here the problem that I posed on Friday, right? We said we were going to pick it up this week by looking at this notional wind turbine. And the example here says, all right, this wind turbine is generating electricity via a gearbox and a generator. Okay, so this first gearbox, or this first box here is our gearbox and feeds into our generator. And each of those components has some finite efficiency. In this case, we're assuming that the gearbox has an efficiency of 93% and the generator of 95%. So, right, 93% of the mechanical power coming in from the blades or from the hub comes out as mechanical power at the other end of the gearbox, just at some different shaft speed, and then 95% of that mechanical power comes out as electrical power. And at the end of the day, this thing is producing 2.5 megawatts of power at steady state. And we're assuming that it's all enclosed inside of this idealized cylindrical shell, right, the nacelle, as they call it, that is 6 meters long and 3 meters in diameter. And we're asked to find how much thermal energy per unit time is actually being transferred out of this thing, right, in order to maintain steady operation. And then what is the rate of energy dissipation per unit surface area, or as we've learned to call it, the heat flux, right, through the surface of this nacelle. So to solve this problem, we need to turn to, right, let's go ahead and say, what governing equations are we going to be falling back on? And that is quite simply the first law of thermo, right? So let's go ahead. Remember, we've got two different versions of the first law. There's the one dealing with total energy, okay, or E total, and then there is the one dealing with thermal and mechanical energy, right? So in this case, let's go ahead and just, let's work with the total energy version. So that is the E stored total, right, dot to indicate rate of change, and we expect this to be equal to 0. Because we are assuming that this is, right, part A, our key word here is steady operation, steady. We are not accumulating energy, the thing is not heating up. Right, so E total in minus E total out. And we're going to go ahead and assume here, right, since we're dealing with total energy and we have a closed system. Why is it a closed system? Because this nacelle, right, is a closed volume. It is a box. And the key thing that tells us is that there's no fluid flowing in and out, right? There's no mass transfer between the inside and the outside of this housing. So our only two ways of getting energy in and out are heat transfer and work, right? Where there's no advection going on. So we've got our Q and minus, right, work rate out. So let's first look at, okay, what is the rate of work leaving? Now, this is a little bit of a less obvious step we're going to take, but we actually are going to group that electrical power that's coming out of the thing, right, as being work in this case. It is current at some voltage potential. And so while it may not be mechanical power, we can effectively group it into the same thing. The other way we could do this is by having that the energy generation term, but we're not going to mess around with that for right now. So we'll go ahead and say that we've got work out is equal to P electric, which is our 2.5 megawatts, which is going to be equal to the actual mechanical work in multiplied by the cumulative efficiency of the generator and the gearbox. Okay, so what do we use this expression for then? We are going to be looking for that total work in, and from that, everything that's left over, whatever's however much this cumulative efficiency is less than 100%, that leftover power is just going to be the inefficiencies that convert it into thermal energy. And that's what we're going to have to dissipate, to get rid of through some sort of heat transfer process through the nacelle to keep this thing at a steady temperature. So we could say that the mechanical work in is equal to, that P electric divided by eta gen times, eta gearbox. So there's our 2.5 megawatts divided by our 93% and our 95%. We'll leave it there actually in, we're going to work with it in a symbolic form here first. So we'll plug this all in at the end, all of our numbers in at the end. So our net work out, sorry, I should net out, Our net work out is going to be simply no, this is the actual the work that is leaving. Okay. The idea is that in our governing equation there, this is our net heat transfer in and our net work out. And so this is going to be whatever work enters or is done on the system per unit time minus or whatever leaves the system per unit time minus that enters. So this expression right here. Okay. So this is going to be our 2.5 megawatts minus our 2.5 megawatts over our we'll just eta gearbox times eta gen. So what this quantity is going to give us, is basically, we can see by inspection that as long as these are less than 1, and they both are, this value is going to be larger, and we're going to end up with a negative quantity. Okay, what does that tell us? It tells us there is more mechanical power in than out. So we're going to end up with a negative net work out. Combined with the negative sign in our first law here, that means, look at that, we've got a positive quantity on the right-hand side, which tells us that we are going to need a negative quantity for Q in, which makes sense. That's our heat leaving, or our thermal energy leaving. So Q in then has to equal, minus net out must equal 0. Q in equal to U net out, which is going to be equal to, right, our 2.5 megawatts times 1 minus 1 over eta gen times eta gearbox. And now, if we plug in these expressions, right, our 93 and 95%, or 95 and 93%, doesn't matter, we are going to end up with a cumulative rate of heat transfer that is 3.3 times 10 to the 5th watts. Okay, so we've got about, what's that, 330 kilowatts of power that is just, right, being dissipated. Right? That's the thermal energy being generated by the inefficiencies in our gearbox and our generator. So that's quite a bit, actually, right? That's 300, almost a 400 horsepower heater, basically. So here's our solution to A. The next question is, all right, that's a lot of power that needs to be dissipated to keep this thing from cooking itself. What does that turn into in terms of the rate of heat flux through the surface of our nacelle? And the reason we might be interested in calculating that is that gives us kind of the link between what we're going to talk about later today, which are the modes and the rate equations for different types of heat transfer, and sizing our nacelle so that we can actually achieve a reasonable heat flux to make this happen. So our Q double prime, okay, and here we're going to go ahead and put a bar over it to indicate that this is our mean heat flux signed positive out. Remember, heat flux is a vector quantity, right? And so in this case, we're going to assume that we are dealing with the heat flux directed along the normal vector of our surface, so it's always producing heat transfer out from the nacelle to whatever the surroundings are. Is equal to Q divided by, right, the surface area. And we're going to go ahead and put a negative sign in front of that for the simple reason that this should be signed positive for flow out, and this is our Q in. So we're just going to put a sign on that. So it's Q out over our total surface area, which is our, right, 330,000 watts divided by, okay, here's our pi times 3 meters times 6 meters. It looks like I forgot the end caps on there. Or are we assuming that it doesn't have end caps? Yeah, let's go ahead and throw the end caps in there too. Plus pi times 3 meters squared. And then since we have 2 of them, 2 end caps, we'll divide that by 2 instead of by 4. Okay. So we're treating this, remember, 6 meters as a 3 meter long by 3 meter diameter cylinder, or 6 meter long by 3 meter diameter cylinder, and we're just looking at the total surface area of this. Bear with me for a moment. I need to, if anyone's got a calculator handy, you go ahead and compute that, because I left my phone back in my office, and I only have the version that doesn't include the end caps. So let's see. Pi. Okay, I think I've got the answer actually. So from this, I am getting a net heat flux of about 4,600, just under 4670, 68.5, right? Watts per meter squared. Is that, hopefully that agrees with what the calculator laden among you have. And so that gives us like a hard number, right? That's also a pretty high number. At least it seems that way, right? We're talking about 4.6 kilowatts per square meter of surface area, which really does appear to be a fairly hefty amount of thermal energy. I want us to just kind of keep that in mind. We'll make some value judgments later about whether that is actually a realistic or unrealistic rate of heat transfer after we kind of understand the heat transfer tools that are at our disposal, right? Those different modes that we're going to be considering in this class. All right. Do we have any questions about how this little example played out? Yeah. Yeah. Oh, sorry, that should be a negative sign on there. Was that, all right. Yes, good catch. Sorry, in my notes I solved for Q out, and I tried to flip the signs on the fly here. Okay, so I've been talking about, like, we kind of worked from the mechanical side, forward here. The question is, now that we have like a target, for this heat flux, and we know how much heat we have to dissipate, the question is, how do we actually get that thermal energy out at that rate? And that gives rise to what we call the rate equations. These are equations that relate quantities like our heat flux or our mean heat flux or the total heat rate, okay, to something that describes the surroundings, okay, the actual environment in which we're operating. So bear with me for one moment. So that is the topic of today, rate equations. And modes of heat transfer. I would love for that to not be hidden. Okay. So our objectives are fairly simple today. We want to understand the rate equations for the three modes, which are things you have already heard, right, or heard about: conduction, convection, and radiation. All right. So this is going to be today's a very high-level overview of these three modes. We are then going to basically divide the course into three sections and go through each one of these in much greater detail. But this is to give you the kind of the bird's eye view of how these work and how they fit into this idea of, like, us living to satisfy that first law of thermo. So at the risk of repeating myself, I want to restate, of sort of what heat transfer is all about. The heat transfer kind of philosophy. that is heat transfer is concerned with how fast, and in what direction thermal energy moves, right, between regions of different temperatures. So I want to underline a few key terms here, right? The how fast, what direction, and the idea of temperature differences. Because each of these is sort of addressed by a key aspect of the course. So there's the how. And this is what we're going to be talking about today, right? This is basically asking, what is the mode of heat transfer, or the mechanism? There is the how fast, which is answered by our application of the appropriate rate equations, which are, generally speaking, these are specific to the modes. So we're going to have a rate equation for conduction, one for convection, one for radiation. The what direction. So if how fast is basically looking for that Q, the what direction comes from that Q double prime, that heat flux. Because it is a vector quantity, and so it not only tells us how much thermal energy is moving per unit time, but the direction in which it's going. And then finally, that idea of the temperature difference, which is sort of imposed on us by the second law of thermo, right? The thermal energy has to flow from hotter regions to colder regions. And so this is where we connect it all with kind of the broader engineering world, because this is our description of the environment under consideration. All right. So our goal today is going to be to answer very broadly, or to address all four of these facets for each of the three modes. So let's start with thermal conduction. So a sort of a physical description of conduction would be, this is energy transfer that's caused by molecular collisions or molecular vibrations. In other words, if we have a medium that is filled with this collection of molecules, be they in a crystalline or lattice structure or something more amorphous. If one end of that material is at a hotter temperature than the other, then on a molecular level, what we've got going on is a whole lot more molecular kinetic energy, right? The molecules over here are going nuts. They are either vibrating or they are zipping around and colliding with their neighbors. And so, increased motion, at the molecular scale. And so what that does, right, is through the process of colliding with their neighbors or shaking their neighbors around, they are imparting some of their energy to their lower energy neighbors, right? And so we end up with this net flow of energy from the hot and therefore more energetic side to the cold and therefore less energetic side. And this conduction, this process of conduction, refers to what we call diffusion of molecular energy from hotter, right? So more energetic, to the colder, less energetic. And here I want to define the word diffusion. Simply refers to the process of spreading. So the idea is that thermal energy is going to diffuse through a medium in the same way that dropping a bit of food coloring into a glass of water causes a diffusion of that color slowly, right? You'll see dye moving from regions of high concentration to regions of low concentration. The same way that smells in a room tend to diffuse through the air in the room. And the actual description of this diffusive process, right, is given by the associated rate equation, which is called Fourier's law. Fourier's law says that Q double prime, right, there's our heat flux vector, is equal to negative K times gradient T. Okay. To kind of make this a little bit more digestible, let's also state the 1D version of this, which would say that Q double prime, for example, in X is equal to negative K times partial X of temperature. So a few things to note about this. Let's box that in. This is an important one. This negative sign here. Okay, what this means, or what this the purpose that this negative sign serves is to ensure that this law, if we have a positive K, our conduction coefficient, that this obeys the second law of thermo, right? So gradients tend to point, right, they do point, not tend to. Gradient is going to give you the net rate of change and the direction in which that rate changes. So inside of a medium, the gradient vector will point in the direction that the temperature is increasing. And since thermal energy flows opposite, okay, from hot to low, we need that negative sign to indicate that this says that heat flux moves the other direction. So in both of these cases, also, I'll say that what we're going to get, right, is just as in the example we did earlier, units of watts per meter squared. So K here is what we refer to as our thermal conductivity. And a T is, of course, right, our temperature. Now, in general, a large value of K means this is a good conductor. For example, K of aluminum is around 237 watts per meter Kelvin. And copper is even a bit higher, 401 watts per meter Kelvin. Small k is associated with insulators. So K of air is around 0.0263 watts per meter Kelvin, and that of water is an order of magnitude higher, but is still only 0.6 watts per meter Kelvin. Okay, so this is a fairly good indicator of why we see, things like thermoses or other, like double-walled coffee cups, where they'll either have a complete vacuum, or over time, those vacuums don't tend to stay very vacuous. You'll end up with air in there. But instead of just having steel or aluminum or some metallic, right, wall that is going to act like this nice thermal conductor, all you need is a thin layer of air between your two walls, right, to arrest that heat transfer through the walls and keep your coffee nice and hot. And so that's a significant chunk of what we need to know at this stage for conductive heat transfer is this Fourier's law. Now, what you'll notice is that this rate equation, this is really just a differential equation. Okay. In fact, it's a partial differential equation. And what we're going to be doing is looking at how we actually solve that differential equation. How do we solve for the temperature differences as well as the heat transfer rate or the heat flux? And what happens when, for example, you have multiple different conductive media stacked on top of each other, right? How do you approach this problem when you insulate the walls of your house, or when you move from a single-walled, hot beverage container to a two-wall with a gas in between them? Let's run a quick example of conduction here. Actually, let me flip over to... Nope. All right. I will... There we go. Okay. I want us to consider this bar of solid copper. A copper bar. It has a cross-sectional area of 1 centimeter squared. Okay. So A is equal to 1 centimeter squared on each face. And here I'm referring to the end faces. Okay. Along all of the longer rectangular faces, okay, all of the 10 centimeter by 1 centimeter faces here, these are all going to be considered as being sort of infinitely insulated. So in our y and our z directions, we can assume that there's no heat transfer going on. Right? The reason we do this is this allows us to boil this down to a one-dimensional problem in x only. We've got, right, this region A and this region B. And we want to figure the heat, yes, heat flux if, right, TA is equal to 100 degrees Celsius and the temperature at B is equal to 150 degrees Celsius. So a good analogy for this might be, we know something that tends to happen at 100 degrees Celsius, right? Water tends to boil. So maybe at A, this is in contact with liquid water, and this is a heating element, right? Or rather, the heat conduction element. And so we have some heater over here that's set at 150, and it's pushing as much thermal energy through this bar and into the water to produce boiling as it can. So that's part A. And then part B is find, right, temperature B if temperature A is 50 degrees Celsius and power is being dissipated from a motor with an efficiency of 90% and a mechanical power output of P is equal to 1 kilowatt. So we've got two sort of separate problems that we're analyzing here. Part A, find heat flux. Second one, we are assuming that this is like a heat sink or a heat pipe, right? Something that is there to move energy away from an electrical device. All right, so for part A, we know, right, that Q double prime X, the heat transfer rate in X is equal to negative K partial T partial X. And we know that K of copper is equal to 401 watts per meter Kelvin. We know this because I wrote it down earlier. And it's one of those values that we can look up in the tables that are in the book. So what we need to do to find our Q double prime X is simply know K. We need to know our estimated partial T partial X. Partial T, partial X. And given what we're given here, how could we estimate that? Are there any thoughts on like what at least a rough approximation might be to the temperature gradient? Or how we might find it? Yeah. Perfect, right? So basically the delta T over, right, that delta X. So our T B minus TA over, right, that 0.1 meter. 500 Kelvin per meter. So now Q double prime X is just a matter of multiplying negative 401 watts per meter Kelvin by that 500 Kelvin per meter, and we get 200,500 watts per meter, right, with a negative sign on there, indicating, in this case, that the thermal energy is flowing from, if X is pointing towards B, right, B is hotter, thermal energy is flowing in the negative direction, in the negative X direction. So X, TB, right, TA. Saying here is our approximated temperature gradient, and here is the rate of heat transfer per unit area. So I want you to bear in mind these are pretty realistic temperatures, right? 150 to 100 degrees. That's not a crazy temperature gradient. Remember our heat flux from the wind turbine problem? That was something like 4,600 watts per meter squared. And we said that seems like a pretty big number. Well, compare it to this one now, right? We've said that a realistic temperature gradient through copper is actually going to produce something like 30 times that heat flux. So that gives us a little bit of a reality check that maybe that heat flux in 4,600 watts per meter squared for the casing on this this wind turbine isn't quite so crazy after all. This is also a pretty good indication of why copper is used for heat conductors, like why you have copper paste for attaching heat sinks to electronic devices, etc. Yeah.
Is it going to be in watts per meter or watts per meter squared?
Sorry, I left out my superscript. That is absolutely watts per meter squared. Thank you. Okay, part B. You know what? Actually, part B, for the sake of time, we'll come back and we'll use part B as a warm-up. We're going to go ahead and continue this on Wednesday because I want to at least give a little bit of airtime to convection and radiation instead of leaving them totally undiscussed. So convection, right? Is the transfer of energy by a moving fluid. And it's actually an amalgamation of two different heat transfer processes. Convection it's a mashup of those terms too. Right? We can imagine that an item placed into a fluid is going to transfer some of that heat through conductive heat transfer to that fluid, right? Makes sense. We have a K value for air and for water. Plus the process of advection, right? The bulk motion of a fluid that just carries energetic fluid to other places. And so this conduction, right, this is purely molecular motion. And so this tends to dominate very near surfaces, something that from fluids we should understand as being the boundary layer, right, where we have like a non-slip boundary. Fluid is in contact with the surface. It has to have the same velocity as that surface. Therefore, it can't move and advect energy away, so heat, thermal energy gets conducted to those fluid particles. Plus, right, the bulk fluid motion which is dominant far away from surfaces. So I mentioned fluids, and actually there's some shared DNA between convective heat transfer and fluids, especially in some of the language we use. So for example, in fluids we had this idea of, so if we have some surface, we'll say it's at some temperature Ts, and if we have some fluid moving past it at some velocity u infinity, sorry, those should be connected, then between the surface and far away we have this, right, this boundary layer. In heat transfer, we're going to qualify this a little bit, and we are going to say, hey, this isn't just any old boundary layer, this is known as the velocity boundary layer. Okay. There's that region of change between the velocity of the surface, in this case 0, because fluids have to have continuity of velocity, and the free stream velocity, producing this continuous gradient. And we also, right, if our fluid is at some temperature, T infinity, then guess what? We also have, well, usually it's going to be colder. We're going to have some thermal boundary layer that develops as well. So the rate equation, right, that describes how heat transfer occurs between a surface and an adjacent fluid is known as Newton's law of cooling. And this says that Q double prime is equal to H times Ts minus T infinity, right, directed along the surface normal vector. So that means, right, normal vector pointing away from the surface. And this one seems nice and easy, actually. There's no derivative term here. This is just a difference, okay, which is awesome, right? No partial differential equations. The thing is, this H is doing a lot more heavy lifting in this equation than the thermal conductivity in the conduction equation. That's because H is going to depend on things like how fast the flow is moving, what flow it is, what the velocity boundary layer looks like, what the surface itself looks like. This is very tightly coupled to the fluid flow. And so we're going to spend the middle third of this class estimating this H. All right, we will come back on Wednesday and do a little bit of a survey of radiation and a couple more examples, and then start hitting conduction hard. So